My name is Rayyan, and the problem we aim to solve is by designing and building a rover capable of navigating a complex maze. The rover must be able to identify its position and orientation within the maze, move to a designated loading zone to pick up a block, and deliver the block to a specified drop off point. The challenge lies in ensuring the rover can adapt to being placed in a random starting position, therefore requiring robust localization, pathfinding, and obstacle avoidance capabilities. Now, the problem is relevant because it reflects the real world challenges in both robotics and automation. Navigation is a critical component in several industries, such as the automotive, manufacturing, or even search and rescue operations. The project not only promoted innovation and problem solving, but also gave us that practical experience into sensor integration, algorithm design, and hardware software communication, all of which are essential skills in solving the complex automation tasks of the future.
Manual operation of unmanned vehicles is crucial in unpredictable environments like mining and rescue missions where the path is unknown and conditions are unsafe for humans. While automated systems excel on predefined paths, their effectiveness reduces when paths are uncertain and environmental conditions are unstable. We aimed for a simple yet effective solution that meets design and budget requirements. Our team created a manually operated robot controlled by a PlayStation controller and equipped with a digital body sensor map. This map matches the robot's physical structure and displays sensor readings at the sensor locations on the robot. Moreover, user experience often poses challenges with automated systems, emphasizing the need for intuitive and adaptable designs. Our solution tackles the perceived complexity of automation and the loss of control, ensuring a user-friendly approach in real-world applications.
Our team collaborated seamlessly on all parts of the project. This included the software, electrical, and mechanical aspects in which a designated expert was assigned to a specific area. Jibrail led electrical wiring and soldering, I focused on programming and driving, Genevieve handled mechanical design and 3D printing, and Leen worked on the assembly and electromechanical integration. We used Discord as our primary communication platform to brainstorm ideas, debug issues, and work on the report. This cohesive approach amongst the team members ensured the project's success.
During our project, we encountered significant challenges, mainly with power integration. Initially, we struggled to provide enough power to our motors, Arduinos, and our Bluetooth module. This led to issues where the servo motors for our gripper system could not execute commands, causing the board to shut down and for us to lose Bluetooth connection. To resolve this, we implemented a buck converter to step down 12 volts to 5 volts for the servo, ensuring sufficient power for both the motors in our drive system and the motors in our gripper mechanism. Another challenge we faced was addressing the errors and bias in our drive system. We tackled this using a PID controller in our motor programming logic to eliminate signal errors and to ensure that the robot can travel in a straight line over long distances. So once this issue was resolved, our team was able to adjust and increase the speed, allowing for the robot to navigate the maze more efficiently. And additionally, we customized a gaming console app to remotely control the rover. So this enhancement improved our user interaction and control precision, making the overall operation of our rover more intuitive and effective.
During Milestone 1, we addressed refresh rates and obstacle avoidance challenges by identifying the sensor with the longest distance and orientating the robot in that direction. Blind spots were mapped on the sensor placements, and zonal logic was implemented to interpret specific ranges of sensor data for navigation. During this stage, we encountered issues with infinite loops and conflicting logic, where speed emerged as the primary blocker. During Milestone 2, we navigated a maze in 6 minutes using a compass for orientation. The robot was initially orientated north, and the sensor readings were used to estimate the position in the maze. Navigation was achieved by aligning the robot with the sensor detecting the longest distance and using readings to identify zones or landmarks within the maze. This approach allowed us to command the robot to specific locations. However, motor bias presented a significant challenge as the robot often struggled to travel straight or rotate precisely. Manual operation was critical in identifying which motor exhibited greater bias and determining the safe travel distance with minimal deviation. Finally, for Milestone 3, we implemented a PID controller to correct motor bias and minimize error. The robot speed was adjusted to allow faster maze travel while maintaining sufficient control to avoid collisions in tight spaces. This balance of speed and control ensured effective navigation and completion of the task within the maze in under 4 minutes and 18 seconds.
On to the takeaways. Spending more time on power integration and reducing the sources of power for the entire system is something we would have loved to explore further. If you could power both Arduino boards and the motors with the 12-volt supply, it would have saved the cost of an additional 9-volt battery. We also wanted to use histogram localization to enable automated control or even some sort of driver assistance to correct human judgment errors when in manual mode. Implementing acceleration and deceleration would have also been beneficial, as this would allow for smoother driving. Finally, to improve the user experience, we could have used 2D mapping paired with the histogram that would display the rover's heat map. But overall, I'd say the Roadrunner did pretty well. Thank you.